All right, good morning, everyone. Just hit the record button, so we are recording now. What we're going to do today is we're going to continue on with our discussion of vectors, and we're going to talk about a product, a particular kind of product on vectors. This is the dot product. Most of this discussion can translate to arbitrary dimensions for vectors. And so we're going to talk mostly about three-dimensional vectors, but you can carry on this discussion with four-dimensional, five-dimensional, and so on. This is in contrast to the second kind of product we will look at for vectors, which will be next lecture, and that's the cross product. The cross product of two vectors is really only a quantity defined in 3 dimensions. So that's our contrast with the cross product. But both the dot product and the cross product are going to help with figuring out the geometry of vectors in 3 dimensions. So here's our motivating problem. We've got 2 vectors in space. In this case, it's 3 dimensions. So 3, 0, 4 is vector A, and 0, 4, 3 is vector B. And what we'd like to do is we'd like to find the angle between those 2 vectors. So what is our angle between vectors A and B? So let's get a little picture here. I'll draw my X, Y, and Z coordinate axes. Vector A has components 3 in the X direction, 0 in the Y direction, and 4 in the Z direction. So I'll just draw some reference lines here. So that'll be 3, this will be 4, and there's our vector A living in the XZ plane. And then our other vector B is 0 in the X direction, 4 in the Y direction. So 1, 2, 3, 4, and 3 in the Z direction. So we'll draw some reference lines there. And there's vector B. And what we'd like to do is find the angle between them. So I'll zoom in a little bit here. We'd like to find the angle between these 2 vectors. So that would be this angle here. And that's our question. What is the angle? At this point, we don't have the tools. You might have studied the dot product already in another course, for example, in linear algebra, and you might know its relationship with the angle. So you might have the tools at this point. You might not. And so we're just going to go along the lines of, if we don't know how to find the angle, we soon will, and we'll see how it's related to this quantity called the dot product. Now, one other thing I want to point out at this time is we do play a lot in 3 dimensions in this course. And so being able to visualize in 3 dimensions and do sketches like the one I've got there, that's going to be important. But there'll be times when you just want to plot some stuff in 3 dimensions and have a different viewing angle and drag things around and look at it. And so I just want to bring your attention to a wonderful tool. It's online, it's math3d.org. So as soon as you open it up, you get to a window like this. This page is written and developed by a mathematician in the States. He just wanted a tool. He teaches vector and multidimensional calculus, and so he just wanted a tool that his students could go to and start graphing. It's built on another open source package called MathBox, and that's just a set of libraries for doing 3D plots in JavaScript. So if you're a computing science person, then some of those things might be familiar to you. But the idea is this is all built on open source software, and it's very nice because you open the browser page and there you are. You're able to interact with a 3D window. So what we're going to do is we're going to plot those vectors just to see how we can get a visual for this. So when this page first opens, we're given an explicit surface, and that's just the prototypical example that's open. So you can click the X button next to it, and that'll close it down and leave us with a fresh page. And then we can go to Add Object. It's a long list of objects. We'll in fact use most of these objects throughout the course of the term. For us, we're going to be interested in this vector. So we click on the vector, and it gives us this model of a type of vector. It's just 3, 2, 1, and so we can go ahead and change these numbers. And I can also change the name that's given here. So maybe I'll call this vector A, just so that when I refer back to it, I know which one it was. The vector A is 3, 0, 4. And there it's plotted, vector A. And based on our notes, the way we've drawn it, we sort of oriented our axes this way. X was coming out of the page, Y was going to the right, Z was going up. So that was our vector that we drew. We colored it in pink, so let's do the same thing. So notice if you click on this circle, it hides or shows it. But if you do a long press on the circle, then a palette opens up. I don't have a choice of pink here. Maybe I'll choose a purple instead. And so there's our vector A. Now, one of the things I did talk about when we were talking about vectors is vectors don't have a place of origin. They don't have a specified point that they have to always emanate from. This vector A, 3, 0, 4, is just the arrow. It's got a length and it's got a direction. It doesn't have a place of origin. It just so happens that the software always just plots them at the origin, but we could move them around. So if we click the gear icon, and there's this option of where do you want it to start from? What do you want its tail to be? So we could move it around. I can make it 1, 1, 0, and that's where my tail is going to be. And so then I hit enter, exit it out, and now I can see that the vector has now a tail starting at 1, 1. Same vector, same components. This is vector A. It's been drawn to start from a different location, but it's the same vector. Okay, so for us, we'll be interested in 0, 0, 0. In other words, we'll be thinking of it as the position vector in this case of its tip, which is 3, 0, 4. And now we need to plot another vector. So the other vector is going to be 0, 4, 3. So 0, 4, 3. That's our vector B. And we can color, I colored it blue in my notes, so we can leave it as blue. So these are the two vectors we're interested in. If we wanted to label them too, you can go under the gear icon. You could label it. I could label this one A. And I think there's a show label. Label visible, yeah, I've got to click that on so that it shows the label. And there's the A, and then I could label B if I wanted to make sure I show the label and close it down. So now we can see the A and the B. What we're interested in, and this is the motivation for this entire section of the dot product, is what is the angle between these two vectors? So what is this angle here? That's what we're trying to find. Okay, so now we got a visual for what these vectors are. Now we're going to try to see if we can figure out how to get the angle between them. So I'll just move this back to my other screen. Okay, so that's our motivating problem. Now I'm going to introduce the dot product, and by no means is this clear why this dot product that I'm going to define has any relationship with the angle. That is not clear at all from this definition. So what is our definition of the dot product? Two vectors, A and B, have a dot product defined by taking the product of each of their component values and adding them up. So we take, for the dot product, we take the x component value for the first vector, the x component vector for the component of the vector for the second vector, multiply those together, and do that for the second component, a2 times b2, a3 times b3, and add them all up. So that's what the dot product is. It's this scalar. So this is known as the dot product, also known as a scalar product. The reason it's called a scalar product is because it takes two vectors in and produces a scalar as a result. So this is a real number out. This is something to keep in mind. The dot product produces a real number output, also known as a scalar. So this is a scalar output. As opposed to next class when we introduce the cross product, it takes two vectors in and produces a vector as an output. Okay, so the dot product takes two vectors, produces a scalar. And what we want to do is make sense of what this scalar is. What is this number that we get out? How is it related to the original two vectors? What can it tell us about the geometry? So as a first example, let's just actually compute a dot product. So A dot B, that's 5, 7, 0 dot -3, 4, 2. And the dot product is multiply their first components together. That's 5 times -3, which is -15, plus the second component, 7 times 4, which is 28, plus the z components, 0 times 2, which is 0. So this has a value of 13. So that is our dot product of those two vectors, an example of computing. What we want to figure out now is, what does this number 13 represent? What does it mean? Does it have some relationship with the angle? Does it have some relationship with lengths of vectors? What does the 13 mean? How can we interpret that value that came out of this dot product? In order to get to that, we will first cover 5 properties that the dot product have. These are all algebraic properties of the dot product. So what are some of the algebraic properties the dot product have? How can we work with the dot product in practice? So the first property of the dot product is if you take a vector and you dot it with itself, what that returns is a square of the length of the vector. And this is not too hard to see, because if we again, pretend we're in 3 dimensions, all these ideas sort of extend to arbitrary dimensions, but we'll just focus on 3 dimensions. If I take the dot product of A with itself, then I just get A1 squared plus A2 squared plus A3 squared. And that's just the square of the length of the vector, because the length of the vector is the square root of that quantity. So this is the square of the length. So that's that first property. Just follows from our definition of length and our definition of dot product. The second property of dot product says it doesn't matter which order you dot 2 vectors. You can take A and dot it with B, or you could take B and dot it with A. Either way works. It's commutative. Order doesn't matter. And that's because the underlying multiplication that you do, if I scroll back up to the definition of the dot product, it doesn't matter which order you multiply 2 real numbers in. If you take A1 times B1, or if you do B1 times A1, the answer is still the same. So because multiplication is commutative, the dot product is commutative. We also have that the dot product distributes over addition. So if I have a vector and I dot it with the sum of 2 vectors, I can distribute it across. And I get A dotted with B plus A dotted with C. So this is known as the distributive property. I'll write that down here, distributive property. And then how does the dot product relate with the scalar product? So we already had one type of product, sorry, the scalar multiple, I shouldn't say scalar product because the dot product is a scalar product. How does the dot product relate to scalar multiplication? So this is where we take a scalar and multiply it to a vector. And so here's 2 equalities or 3 quantities that are all equal to each other. If we scaled A and then dotted with B, that would be the same as dotting the 2 vectors first and then scaling them after. Or it's the same as scaling B and then dotting it with A. So this tells us that we can scale either of the 2 vectors first, or just scale the result of the dot product, and you get the same answer in all 3 cases. And lastly, if you dot a vector with the 0 vector, then you get the 0 scalar. So you get a 0 as a real number. So those are the properties of dot products. And in fact, these are the properties that are going to allow us to interpret the dot product as some geometric quantity, something that tells us some things about the geometry of the vectors and how they sit in space related to each other, the angles between them, how they project onto each other, all those sorts of goodies. So that gives us this first geometric interpretation of the dot product. So if theta is the angle between the vectors A and B, then it turns out that the dot product and the angle are related by this expression, that the dot product of A and B is precisely equal to the length of the two vectors times cosine of the angle between them. And we're going to prove this. So I want to prove this because I want to show you how these properties that are written above in the blue box or the purple box, how we can use those to get expressions like this. The other reason I want to prove this is because it's a nice application of the cosine, the law of cosines, which law of cosines you probably learned in trigonometry, maybe back in grade 11, maybe back in grade 12. If you're like most people, you learn the law of cosines and then you quickly forget it. In some sense, the law of cosines is just a generalization of the Pythagorean theorem. The Pythagorean theorem, I know you all know, I know you all know and probably use quite frequently. The law of cosines is just the generalization of the Pythagorean theorem in the case where we don't have a right triangle. So if it's a right triangle, the Pythagorean theorem tells us how all the sides lengths are related to each other. In fact, it tells us that the square of the hypotenuse is the sum of the squares of the other two sides. The law of cosines tells us how the side lengths all relate to each other as well, but with the addition of an angle as well, because we're assuming that it's not a right triangle. So there's got to be some angle that we're going to be using as well. So I'm going to write down what the law of cosines is. We're going to prove the law of cosines just as a refresher, just so I don't want to use a formula from your past that you may or may not have remembered and then just say, oh, you know, here, we're going to use it as a fact. No, we can prove it. We have the tools to prove it. So I'll be honest, I don't most of the time remember the law of cosines, but I derive it whenever I need it. And so I want to show you that we can always derive this quantity whenever you need it. So the law of cosines. So what we're going to do is we're going to start with a triangle. And I'm just going to start with two side lengths. And then maybe we'll look at it like this. So there's our arbitrary triangle. I don't want it to have a right angle. It kind of looks like it does up at the top there. So maybe I'll extend this a little bit more. There we go. Maybe that's good enough. I don't want any of my angles to be a right angle, so I didn't want that one at the top, which kind of looked like a right angle in my last drawing. So here we've got a triangle. I've got a length A. Now here I'm just thinking these as lengths, so I'm not going to put vector signs on top of them because this is going to be deriving the law of cosines from principles that we've developed in like grade 11 or grade 12. And we've got a length C. And I'm going to pick two of these sides and write down the angle between them. So there's our angle between them. That's our theta. And now what I want to do is come up with a relationship between A, B, and C and this angle theta. In the case where it's a right triangle and we would, in a sense, be deriving the Pythagorean theorem using this method, that angle would be the 90-degree angle. But here we're assuming that that angle is not 90 degrees, so it's just some other angle. So how are we going to get a relationship between those sides? Well, the first thing I'm going to do is I'm going to drop a perpendicular down. So I'm going to drop a perpendicular down from this point up here down to this edge, which has length B. And the reason I've dropped this perpendicular down is because now I have two right triangles, and I can use the Pythagorean theorem on these two right triangles. So I'm going to derive the law of cosines from the Pythagorean theorem. And if it helps, we can throw a set of coordinate axes in as well. Maybe something like this. So that's our x-axis and our y-axis. That might help just sort of position this thing in space, and we have a frame of reference to talk about points and things from. All right. So now the very first thing I'm going to do is I'm going to work on triangle number 2. And I'm going to say, well, triangle number 2, it's a right triangle. So I know that there's a relationship, and I'll draw this line out here so that I can talk about that height as well. So for triangle number 2, I know there's a relationship between that purple length, that blue length, and the length C. That's the Pythagorean theorem. So then I just need to know what is the purple length and what is the blue length. Well, that's where I look at the first triangle, the triangle with the A as sort of that hypotenuse of it. For that first triangle, this distance here, can anyone tell me what that distance there is? You look at that first little right triangle, A, angle theta. What's that distance? What's that horizontal distance, or that distance along the X? Yeah, you got A cos theta. A cos theta is that distance there. And then someone else wrote in the chat that this is going to be then the full distance B, minus that short little distance A cos theta that we took off. Okay, so that's the length of the blue segment, B minus A cos theta. So just using a little bit of trigonometry here. The height, that length of that purple line segment, what is it? Yep, you got it, A sine theta. So this is A sine theta. And now we can use the Pythagorean theorem. So Pythagorean theorem on, I'll say it this way, on triangle number 2, that blue triangle. And what the Pythagorean theorem tells us is that the length of one leg, A sine theta, all squared, plus the length of the other leg, B minus A cos theta, all squared, is equal to the square of the hypotenuse. So that's equal to C squared. So that's the Pythagorean theorem on that triangle 2. And now we can just unpack it. So this is A squared sine squared theta plus, and expanding out that next one is B squared minus the cross term 2AB cos theta plus A squared cos squared theta is equal to C squared. So we just expand it all out. And then we make a couple of notes here. We note that I've got an A squared cos squared and an A squared sine squared. Those two can join together to just give me an A squared, because sine squared plus cos squared is 1. So that gives me an A squared. Maybe I'll draw little arrows at those two combined together to just give me that A squared. And then I got plus a B squared and a minus a 2AB cos theta is equal to C squared. And this is the law of cosines. The law of cosines tells me that the lengths of the 3 sides of that triangle satisfy the property that A squared plus B squared, where A and B are the lengths that make up that angle, or the 2 sides that come together at that angle theta. So it's A squared plus B squared minus 2AB cosine of the angle between them is equal to C squared. In the case where theta is 90 degrees, cosine of theta would be 0, and this would just become the Pythagorean theorem. A squared plus B squared minus 0 is equal to C squared, or A squared plus B squared equals C squared. So that's the law of cosines. We've just derived it now. I'll put that in a little bubble here. This was just our tangent into trigonometry. So grade 11, grade 12, wherever you would have learned this. That's the law of cosines. That's the one we're going to use now, because now we can see that what this law of cosines does is it relates lengths of sides to the angle between them. And that means there should be a relationship between lengths of the vectors, if we think of the sides as being made up of vectors, lengths of the vectors and the angle between them. So let's go ahead and now draw a picture and use this law of cosines. So here's our corresponding picture. I've got 2 vectors, A and B. Let's just assume they look like this. And we got an angle between them. That's theta. And I want to relate that angle to the dot product of the 2. So what I'll do first is I will put in my diagram the vector B minus A. So maybe take a moment just to refresh your memory from last lecture. Draw B minus A in this diagram, B minus A, and put it at the ends of the vectors A and B. So connect the tip of A and the tip of B in some way with the vector B minus A. So yeah, in this case, b minus a is going to be this vector here. It's going to go from the tip of A to the tip of B. So that's b minus a. And if you want to double check why that's the case, run around two of the sides by following the arrows they point in. So if I go along A and then follow b minus a, then what I get is a plus b minus a, or just the vector b, starting from the tail of A, ending at the tip of the green vector, and that is the vector b. Another way to think about b minus a is it's the tip minus the tail. So b is the tip and a is the tail. So however you want to think about it. Then there was a question in the chat to find the vector that joins a and b. Yeah, so in this case, in order to do this or prove this formula, the geometric interpretation, that's exactly what we're going to do. Yeah, we're going to find the vector that joins the tip of A and the tip of B to form this triangle. And then we're going to use this diagram and a law of cosines to get the angle. You got it. So now what we'll do is we'll use the law of cosines to relate side lengths and the angle. And so what is the law of cosines? I'll write it in this way. It's the side opposite the angle, the length of that all squared. So that's b minus a in magnitude all squared. And that's going to be equal to the length of the two sides, the sum of them squared. So length of A all squared plus the length of B all squared, minus 2 times the length of the two sides, A and B, times cosine of the angle between them. And so that's what our law of cosines gives us for that diagram on the left. Okay, so I'm just using the law of cosines now to relate the side lengths of those three sides of the triangle and that angle, that one angle that we are interested in. And now what we're going to do is we're going to just use our definition of length and its relationship to the dot product to figure out how to reduce these expressions. So for example, b minus a in magnitude all squared, well, that's just b minus a dot b minus a. So that's that first one, b minus a dot b minus a. So here is where I've used this expression here in my properties to go from there to there. I just used it instead of for the vector a alone, I used it for the difference, that vector b minus a. So b minus a magnitude all squared is just the dot product of b minus a with itself. I'm going to leave a magnitude of a squared and magnitude of b squared alone. I'm not going to write them as a dot product. I could, but I'm just going to notice that they appear on the right hand or the left hand side anyway, and so they're going to cancel out. So we'll see that in a second. And again, I'll leave these as magnitudes as well. And the reason is because I already see that the formula I'm trying to prove has a magnitude of a, magnitude of b cos theta appearing on the right hand side. I'm trying to show that that's equal to the dot product. And so I want to leave that magnitude of a, magnitude of b cos theta alone because that's what I want in my final formula. Okay, the next step then is to use our distributive property. I have this thing dotted with b minus a, so I would distribute across. And then I would do the distributive property in the opposite direction. So I'm going to break this up into 2 steps. Normally I would just do this all in one go, but I'm going to break it up into 2 steps, and we're going to use the distributive property here. So what does this property tell us? If I look back up into the third equality in my properties of the dot product, it says that I can take a vector being dotted with a sum and just distribute it to each of those vectors. So this would be a b minus a, which is my vector that I'm distributing across. It would get dotted with b. And then I would, minus the same vector, b minus a, dotted with a. So that's the distributive property being used to distribute that vector b minus a across that difference. And then I get the magnitude of A squared, magnitude of B squared, minus 2AB cos theta. And now what I'll do is I'll use the distributive property again. I'm going to distribute this vector B across that sum, and I'll distribute the vector A across this sum. And you might say, well, when you look back up at the properties of the dot product, there isn't a distributive property that tells us if we've got a sum dot a vector, you can distribute it across to the left. But that's just a combination of the second formula that says if I have two vectors A dot B, I can reverse their order and get B dot A. So this distributive property going in this direction from right to left is really just a combination of the distributive property written above and the commutative property right above that, A dot B equals B dot A. Okay, so now this gives us that B dot B minus A dot B. So that's the distributive property on that first one. And then we get a minus B dot A, and then a plus an A dot A. So that's that whole thing expanded out. So that was the whole length of B minus A all squared, fully expanded out in terms of dot products. And that's equal to the magnitude of A squared plus the magnitude of B squared minus 2 magnitude of A, magnitude of B, cos theta. Okay, and now we get some cancellation. This is where we can see some stuff is going to cancel. So B dot B. B dot B is just the magnitude of B squared, and that appears on the right-hand side. So I get that that is going to cancel with that because they are equal to each other. Similarly, A dot A is going to cancel with the magnitude of A squared because they are equal to each other. And so this then simplifies down to, I've got an A dot B and a B dot A, but they are equal to each other. So this is minus 2 A dot B. So those two middle terms combined together to give me a minus 2 A dot B. And that's equal to a minus 2 magnitude of A, magnitude of B, cosine theta. And I can cancel off the minus 2's now. And we are left with our formula. A dot B is equal to magnitude of A, magnitude of B, cosine theta. And so that's how we can argue why the dot product is related in any way whatsoever to the geometry of the two vectors. In fact, it's related to their lengths and the angle between them. And the underlying reason why they are related was the law of cosines. Okay, so this is quite a wonderful result because it tells us we can compute the angle between two vectors by doing really nothing more than taking a dot product, which is just a multiplication of corresponding components all added up. So that's quite a remarkable result. It says that the dot product, if you kind of think about it, it's a rather straightforward calculation. And so a straightforward calculation has a nice impact in that it helps us figure out angles. So we can rewrite this last expression as a corollary. If theta is the angle between two non-zero vectors A and B, then the angle satisfies, well, cosine of the angle is equal to the dot product of the two divided by their lengths. So let's go ahead. Oh yeah, absolutely.
Does angle have a dimension?
Does the angle have a dimension? That's a very good question. I love it. That is wonderful. Okay, so does angle have a dimension? Dimension or a unit in some sense. The answer turns out to be, if you think about an angle when we measure in, let's say we're measuring in radians rather than degrees, because radians is our unit of measure in calculus. Radians is a unitless measure. And why is radians a unitless measure? we can see that from, one of the properties that relates angle and, well, let's look at it for, I don't know where I want to write this because it's sort of an aside, but let's just look at an angle here like this, theta. And I'll say that we're looking at a sector of a circle. Let's say we've got R here. And if theta is measured in radians, do you remember what the arc length is? What the length of this arc is? Anyone want to shout it out? Maybe even in the chat. If I have a segment of a circle or a sector of a circle, radius R, what is that arc length? Yeah, you got it, R theta. So R theta is the arc length. So what we have is this equation that says S equals R theta. So let's just, for sake of argument, let's say R was measured in centimeters. Then this would have a unit of centimeters. R would also have a unit of centimeters. And so that tells us that in order for this equation to be valid, theta cannot have a unit of measure, because whatever theta's unit of measure would be, S would have to be centimeters times that unit of measure. And so we call the angle or the unit of measure that we use to measure angles as radians, but there's this subtle point that a radian is a unitless measure. Does that help in answering your question?
Yes, Professor, it does, but I have one more if you don't mind.
Yep.
Is it possible to measure the angle between three vectors in three-dimensional space?
Oh, go ahead.
Say,
Yeah,
if I had a prism, right?
Yep.
Like I had three vectors starting at the same point, but like branching off in different directions, like a prism. So could I measure the angle between them?
We're looking at something like this.
Yes, sir.
Yeah, so I mean, there's a couple of ways you could think about what you might want to capture. There is the angle between these two vectors, which could be one angle you might be interested in, then the angle between these two, and then the angle between these two. So you could get three different angles there that would capture their relationship to each other. But maybe you're more interested in knowing what the elevation is, the elevation angle of this vector is from the plane determined by the other two. So we'll fill in like a plane here between these ones. And maybe what you're really interested in is the angle to the plane between that's spanned by these two vectors. So maybe something like that is the angle you're interested in. In that case, yeah, I mean, yeah, it depends on what angle you're really interested in. But all this would boil down to would be still the angle between two vectors. What I would do is I'd find the projection of this vector, which we'll talk about projection in a second, down here. I get the projection vector into that plane, and then I find the angle between those two vectors to get me the angle I'm interested in, which would be the angle between a vector and a plane. Does that help?
Yes, Professor, it does. Thank you.
You're welcome. All right.
So is it more like that we take the resultant between those two vectors and use that vector to find that angle?
Yes, that's right. Yeah, you got it. All right. So let's go ahead and use this result now. We're going to find the angle between A and B. So we got cosine of the angle theta is going to be A dot B divided by the magnitude of A times the magnitude of B. And so that's the thing we're going to want to compute. So we go ahead and we dot these two. That's 3 times 0 is 0, plus 0 times 4, which is 0, plus 4 times 3, which is 12, divided by the length of A, which is 9 plus 16, and the length of B, which is 16 plus 9. So in both of those cases, that's going to be the square root of 25, the square root of 25. So our result here is 12 over 25. That's cosine of the angle. So that means our angle is equal to arc cosine of 12 over 25. And so there is our value for our angle, which we could compute a decimal use a calculator, compute a decimal approximation if that's what you wanted, but this is the exact answer for the angle between them, arc cosine of 12/25. So that's how we can use the dot product to compute angles. Another nice property about the dot product that comes out of this is that if two non-zero vectors are perpendicular, that means that the angle between them is 90 degrees, or pi/2 radians, and cosine of that angle would be 0. So if they're perpendicular, it means cosine of the angle between them is 0. In other words, the dot product would have to be 0. And conversely, if the dot product is 0, then cosine of the angle between them is 0. In other words, the angle had to be 90 degrees, or pi/2. So that's a nice result, is that the dot product allows us to very quickly determine whether two vectors are perpendicular to each other or not. So let's go ahead and prove this result, just so we can say we proved it. So if the dot product is 0, then that means that the dot product over the magnitude of the two vectors is equal to 0. Because the dot product is 0, the numerator is 0, so that ratio would be 0. And that's equivalent to cosine of the angle being 0, because that's what the cosine of the angle is, a dot b over the length of a times the length of b. And cosine of the angle is 0 precisely when theta is equal to pi/2 radians. And that's precisely the case when a is perpendicular to b. So this little upside down t is read perpendicular. So we read that as perpendicular. So this is an awesome result. How are two vectors perpendicular to each other? Take their dot product. If it's 0, they are. If it's not 0, they aren't. So let's do that then. Check if these two vectors are perpendicular. So we're going to take their dot product. 6 minus 16 plus 10 is our products. And that's 16 minus 16, or 0. And so therefore, A is perpendicular to B. So this is, really one of the results about the dot product that we're going to use almost all the time, that the dot product is really a way of telling whether two vectors are perpendicular or not. Moreover, if they're not perpendicular, then we can use that relationship to the angle above to actually figure out precisely what the angle is then if they're not perpendicular. And then this gives rise now to this notion of scalar projection. So what is the corresponding picture I want to capture with this? It was kind of related to this result down here where I was talking about that blue vector, and if I projected it onto the plane, it gives me that pink vector. I sort of look at its shadow. This is now the information that we needed in order to understand that if we didn't understand it at that point in time. So what I'm interested in, here's the setup. I've got a vector A. I'll just draw it horizontally. And I've got another vector B. And what I'm interested in is I want to know how the vector B, if I was to cast its sort of shadow down onto A, how far does it reach along A? Or another way to say this is, how much of the vector B is pointing in the same direction as A? So I'll draw this in a different color. What we do is we take a perpendicular, we drop it down from the tip of A down onto the vector, or from the tip of B, sorry, down onto the vector A. And I'm really interested in knowing this vector. That's the vector where we're going to call the projection of B onto the vector A. So that's the notation we're going to use for that. And I'd like to know how to compute that. if I have two vectors, B and A, I want to know. So, for those of you familiar with physics, let's say I'm pushing a wagon, or maybe I'm pulling a wagon from its handle. I want to know how much work I'm doing on that wagon. Well, I need to figure out what force I'm applying in the direction that the wagon is moving. I'll also be applying another force, maybe up if I'm pulling it at an angle. There'll be an upward force that doesn't point in the direction of motion, and then there'll be a part of the force that points in the direction of motion. And that's what I'm kind of interested in here. For this vector B, what is the part of it that points in the direction of A? Because there'll be another part of it that points in a direction that's perpendicular to A. So what I'll do is I'll label this vector as well, this perpendicular vector, and I'll call it W. And I'm interested in figuring out what that pink vector is. So what do we have? Well, we have that B, we can now write it as a sum of two vectors. I just follow it around that triangle. It's the projection vector, which I want to figure out what it is, plus the vector W. So all I've done is written B as the sum of two vectors, one vector in the direction of A, one vector perpendicular to A. I don't know what either of these vectors are right now. I don't know how to compute them, but I know I can do this decomposition. And now let's figure out what each of these components would have to be. Okay, so once I've done this, once I've split them up, I'll just make a note where W is perpendicular to A, and the other vector, projection of B onto A, projection of B onto A, is parallel to A. So that means it's equal to some multiple of A for some C. So that's what I've done so far. So I've taken B, I've split it up into two pieces. One that's in the direction of A, so it's some scalar multiple of A, which I called C times A. And then a part that points in the perpendicular direction, which I called W. And now what I'll do is now we will dot this equation with A. We're going to dot it with A. So that means I'm going to take the left-hand side, I'm going to dot it with A, and then I'm going to take the right-hand side and dot it with A. So, and for that right-hand side, I'll rewrite this expression as my C times A. So I don't have to write that messy projection A, B onto A. I know it's in the direction of A, so it's some C times A. So I dot that with A. And then I also dot W with A. So all I've done is taken this decomposition into two pieces and then dotted it with A. And the reason I've done that is because what is this W dot A? What is that going to be?
0.
0?
Yeah, exactly. It's going to be 0. And yeah, Rohan, orthogonal and perpendicular, they're synonyms. Yeah, I'll use them interchangeably. So I might have already, I just do it unconsciously. But yeah, orthogonal, perpendicular, they're going to mean the same thing. So this is 0. And so what we have is that B dot A is equal to C and then times A dot A. And A dot A is just the length of A all squared. So that's what A dot A is. And that means I've figured out what C is. C is equal to B dot A over the length of A all squared. So that is awesome, because what it tells me is that this pink vector right here, projection of B onto A, is precisely this C value, B dot A, over the magnitude of A all squared. That was our C value. That was our scalar multiplied to A. And so we've precisely figured out what that projection vector is. It's the projection of B onto A is B dot A over the length of A all squared times A itself. This scalar in front of the A we can slightly rearrange this. So the bottom line on this I want to just mention is we're finding the projection of B onto A. So I want to know how much of B points in the direction of A. It shouldn't matter what the length of A is. All that really matters is the direction A is pointing is, because I just want to figure out what part of B or how much of B points in the same direction of A. So it shouldn't depend on A's length. So that means I could rewrite this as B dot A, and I'll borrow one of those lengths of A and bring it over here to make that a unit vector. And so the point here is now this is a unit vector. And so the projection of B onto A is B dot A over the length of A. That's how much of it points in the direction of A, because it's being multiplied by a unit vector now. And this is what we call the component of B in the direction of A. This is how far or how much B points in the A direction, or I'll even write it as a unit vector. So that's the length of the shadow, length of shadow, if you want to think of it that way. All right, so we've got the ability now to compute projections of one vector onto another vector, how much of, or what its length of its shadow is, or even what the shadow is itself in terms of writing it as a vector. And that's this projection. So the projection of B onto A is given by this vector here. I'm going to write it this way, just so you see it's independent of the length of A. I'm going to write it as this, borrow one of those lengths, dot it with B, and borrow another one of those lengths and stick it under A, because both of these are now unit vectors. So it doesn't matter what the length of A is. That is incidental. It just gets normalized anyway in the formula. That's why we're dividing by the length of A squared, is because there's two occurrences of A up top. And so we're going to divide by its length twice in order to account for the fact that the length of A does not factor into this calculation whatsoever. It's just how much does B point in the same direction as A.
Professor, may I ask a quick question?
Yeah, go for it.
Professor, in this one, we're considering that W is a perpendicular, right? If we, like when we talk about shadow, technically the light source is like perpendicular and directly above B, right?
Yeah.
Like it's perpendicular to A and above B. So I mean, if it was at a different angle, so for example, W, instead of being perpendicular to A, if it had like a different angle compared to A, would that change? Like,
Yeah,
how would
so
that change the projection?
So that's a good question. So this idea of a shadow is sort of just to conjure up an image in your own mind about what we're actually doing. The idea is, if I have two vectors, what I'm doing is I'm just taking a perpendicular to one of the vectors that passes through the tip of the other. And this is the projection now. That's the projection down onto there. So that's the bottom line of what we're doing, is we're just saying how much of it points in the direction. Or in other words, if we decompose that green vector into two pieces, a piece that's in the direction of this vector, I'll call it A, and a piece that's normal. So it's the right angle here, that's the key part. And to a piece that's normal, it's what is that piece there that points in the same direction? That's called the projection. And this is called the orthogonal projection, or orthogonal to the projection. So there's two components. There's the piece that was projected in the direction of A and the other piece that's orthogonal to that. So good question. All right, let's, sorry, we're out of time. I'm just going to do this quick example because I don't want to leave it hanging. We pretty much have everything here. So we'll do two things. We want to compute the component of B in the direction of A. So that's going to be A dot B over the length of A. That's the thing we're going to compute. And what is A dot B in this case? It's 6 minus 2 plus 4 all over the length of A, which is 4 plus 1 plus 1. square rooted, or in other words, it's 8 over root 6. And then the other part to that is the projection of B. So this is the vector part. First part was how far it points in the direction. Now we're going to make a vector out of that. And the vector is A dot B over the magnitude of A all squared times A. And so this is going to be 8 over, in the above calculation, we had just the length on the bottom. Now we want the length squared. So that's going to be a 6. And then that's times A, which is 2, 1, 1. And so that we could write it as 4/3, 2, 1, 1. And so that's the vector of the projection of B onto A. So we'll end it there, and I'll stick around for some questions.